But first, let us recall the basics of titration. Perhaps you've heard that consuming too much acidic foods can cause health issues, such as chronic kidney disease, kidney failure, inflammation, and metabolic acidosis. Or that using a shampoo that is too basic makes the hair dull by causing it to lose elasticity and to break, and generally by making it frizzy. So how do we check if the concentration of these things are too high, too acidic, or too basic? The answer is titration. Titration is a technique where a solution of known concentration is used to determine the concentration of an unknown solution. Titration is used in laboratory medicine to determine unknown concentrations of chemical interest in blood and urine. Pharmacists use it to develop new pharmaceuticals. It is also used to determine fat content, water content, concentration of vitamins, etc. in food. The most common type of titration is acid-base titration. It is used to know how concentrated the acid or the base is by determining the precise volume of acid or base that will completely react with it. Usually, the reaction that occurs in an acid-base titration is acid-base neutralization. So, how is titration performed? A pipette is usually used to measure the exact volume of the unknown solution to be placed into the flask. A burette is then used to measure the volume of the known solution that will be added to the unknown solution. The solution placed in the burette is called the titrant, while the one in the flask is the analyte. The first step in titration is placing the exact volume needed of the unknown solution using a pipette to the flask. Second is the addition of an indicator. An indicator is an organic dye, which is a color that depends on the pH of the solution. It is called an indicator because it indicates the acidity or basicity of the solution. Some indicators include universal indicator and litmus. However, there are other indicators which are preferred in titrations. We have phenolphthalein indicator and methyl orange indicator. Third, fill the burette with the titrant and make sure that it is leveled off at exactly 0. Fourth, slowly add the titrant to the analyte in the flask. Fifth, gently swirl the flask or use a stir plate to mix the solution. Sixth, stop adding when the reaction is complete. In other words, when the endpoint is reached. The endpoint is reached when the color of the indicator changes. It is preferred if the color remains very light but is constant, meaning it doesn't change anymore even if you swirl it. Ideally, the endpoint should coincide the equivalence point, which is the point at which chemically equivalent amounts of acid and bases have reacted. Seventh, record the final volume of the titrant added. For accuracy, the experiment must be repeated several times to get consistent values for the titrant. After carrying out the titration, we can now play the titration curve. A titration curve is a plot of pH versus the amount in volume of the acid or base added. It is a graphical display of how the pH changes as acid or base is added to the solution during titration. For example, say we have an acidic analyte and a basic titrant. As the base is added to the acidic solution, the pH of the solution slowly rises. Then it sharply rises towards the equivalence point. When a strong acid and a strong base neutralize each other, the equivalence point is equal to pH 7. When either of or both the acid and the base is weak, the number will vary. So now we are going to focus on the strong acid, strong base titration. The strong acids include, while the strong bases are other acids or bases not included in the list are usually classified as weak acids or weak bases. The reaction that occurs in the titration is neutralization. Neutralization occurs when an acid and a base react to form water and a salt and involves the combination of H plus and OH negative ions to generate water. Strong acids and strong bases dissociate completely. The resulting pH is equal to 7, since the reaction between the two does not upset the hydronium ion or hydroxide ion balance in water. Now let's proceed to computations. To know the exact concentration of the unknown solution, we can now proceed to titration calculations. The formula commonly used is MTVT is equal to MAVA, where MT is the concentration of the titrant, VT is the volume of the titrant, MA being the concentration of the analyte, and VA the volume of the analyte. Let's say we have a solution of the 0.5 molar sodium hydroxide, and we want to know the concentration of a 25 milliliter hydrochloric acid. After adding 20 ml of sodium hydroxide, the endpoint is reached. To solve for the concentration of the hydrochloric acid, we substitute the values to the formula. Then, we isolate the value we need to find, in this case, the concentration of the analyte. Using basic arithmetic, we know now that the concentration of the acid is 0.4 moles.
The pH of the solution can also be found based on the values given during titration. First, we have to identify which is the excess. If the titrant added is a larger value than the equivalence point, the titrant is in excess. If the titrant is a base, the formula will be which computes for the concentration of hydroxide ions. If the excess titrant is an acid, the formula will be which computes for the concentration of hydronium ions. This can now be used to compute for the pH level using this formula if you were able to compute for the hydronium ions. If you computed for the hydroxide ions, use these formulas instead. Formulae are similar when the analyte is in excess, meaning when the added titrant has not exceeded the value at the equivalence point. You just have to identify whether the analyte is an acid or a base. There you go, you're ready now. It's your turn to try out these problems. Pause the video while you are calculating, then play it again to know the answer. We have a 32 ml sample of 0.3 molar RbOH. After adding the 27 ml of HI, the solution reaches the endpoint. What is the concentration of the titrant? A 24 ml sample of 0.105 molar HBr is titrated with 0.130 molar KOH. What is the volume of the added base required to reach the equivalence point? What is the initial pH? What is the pH after adding 6 ml of base? And what about its pH at the equivalence point? Since the reaction is between a strong base and a strong acid, the pH value is 7. Thank you for watching. We hope you've learned something from this video.